Welcome to section 2.7, graphs of rational functions. Our focus is going to be on graphing rational functions, but we're also going to talk about points of discontinuity and oblique asymptotes. So on the first one here, we have to graph the rational function f of x equals 2 divided by x minus 3. We talked about vertical and horizontal asymptotes yesterday, but we didn't talk about the x and the y-intercept, so we'll add that to get some additional points so that we can graph the rational function. So the y-intercept you guys are familiar with. The y-intercept is where the graph crosses the y-axis, and that is when the x value is equal to 0. So to find the y-intercept, you plug in 0 for x and solve for y. So 0 minus 3 in the denominator, that would give us, it looks like, negative 2/3. So the y-intercept would be at 0, negative 2/3 for that example. The x-intercept is when you plug in 0 for the y value and solve for x. So if we plug 0 in for y, that would be 0 equals 2 divided by x minus 3. If we multiply by the denominator x minus 3, that will give us 0 still, because 0 times anything 0 is equal to 2. Well, there's no x value there anymore, and 0 is not equal to 2. So in this example, we do not have an x-intercept, okay, which tells you something about the graph as well. The vertical asymptote comes from the denominator, and there are no factors to be canceled, so your vertical asymptote comes from the denominator where it's equal to 0, so that would be at x equals 3, so there's your vertical. Your horizontal comes from the degree, and since the degree on top is 0 and the degree on bottom is 1, your horizontal asymptote is at y equals 0. So based on that information, let's go ahead and graph what we have. We know the y-intercept is at 0, negative 2/3. So we'll just do the best we can in terms of plotting that. We don't have an x-intercept, so we can't plot that. The vertical asymptote is at x equals 3, so we're going to graph a dotted line at x equals 3, indicating that is where the vertical asymptote is. The horizontal asymptote is at y equals 0, so that will be on the x-axis. So that's the horizontal asymptote. And that's really all we have. So we need to find some additional points. So get out your graphing calculators, graph this function, and then just find some additional points that we can plot. So I've already done this, so I'm just going to write down the ones that I kind of picked out from the graph. So when x is 2, y was negative 2. When x was 3, it was undefined, so you should see an error right there. When x is 4, y is 2, and when x was 5, y was 1. So if I plot 2, negative 2, and then 4, 2, and 5, 1, that gives me a pretty good idea. I could get a couple more points in there, but that gives me a good enough idea to kind of sketch this one out. So the rational function, it'll get close to that horizontal asymptote. And same thing, get close to the vertical asymptote. And then on the other side, it gets close to the vertical and horizontal asymptote. So there's a sketch of the graph using the information that we had and that we found. So now let's build off of this and introduce some new concepts here. So we're going to go ahead and graph the rational function g of x equals x squared minus 9 divided by x squared minus 2x minus 3. So really the first thing we need to do is make sure we don't have any common factors. So let's go ahead and factor. We got x minus 3 and x plus 3 divided by x minus 3 and x plus 1. And so what you'll notice is we do have a common factor here of x minus 3. So we're going to go ahead and cancel it. And now when we go to find all our stuff, we're going to use the simplified version of x plus 3 over x plus 1. Now at x equals 3, there's still something going on. It's undefined at that value, and we'll talk about that in just a minute. So let's go ahead and find the y-intercept. So what is the y value when x is 0? So plug 0 in. So g of 0 is equal to 0 plus 3 over 0 plus 1, and that would be 3. So the y-intercept is at 0, 3, so we can plot that. The x-intercept, what is the x value when y is 0? So if we set that equal to 0, we got 0 equals x plus 3 over x plus 1, multiply by the denominator. So 0 times x plus 1 is 0, and then you're left with 0 equals x plus 3, and then you will subtract 3. So it looks like your x-intercept is at negative 3, 0. Vertical asymptote, your factor that's left is the x plus 1, so we set that equal to 0, and we find out that the vertical asymptote is at negative 1. So we'll graph the vertical asymptote at x equals negative 1. The horizontal asymptote comes from the degree. So the degree on the simplified version, they're both 1. Also the leading coefficients are both 1. So therefore the horizontal asymptote is at y equals 1. So we will also graph using dotted lines y equals 1 as our horizontal asymptote. And then we need kind of those additional points. And so when we go to look at those additional points, we will find not all of them work out nice. We have negative 4, which is 1/3. Negative 2 is negative 1. 1 is 2. And then we also find 3 is undefined. You'll get an error on your calculator at x equals 3. And that has nothing to do with what we've done so far. So we'll have to talk about why there's an error there. So let's go ahead and plot what we have. Negative 4, 1, 2, 3. Negative 4, 1/3. So about right there. Negative 2, negative 1. So that kind of gives us 3 points in that region, which is good. At 1, 2, we have a point. And then at 3, we have this error. Well, what happens when our factors cancel, which is what happened at x minus 3 and x minus 3, which is at x equals 3, occurs when a numerator, so we have what's called a point of discontinuity or a hole in the graph. And this occurs when the numerator and denominator have a common factor or a common term. And so we have this hole in the graph, and it's a single point, and we got to figure out where it's located. Well, normally when we know where a point is, when we know that the x value is 3, we just plug it in to find out what it is. But when we plug it into the original, it's undefined because you can't divide by 0. So we actually don't plug it into the original. We will plug it into the simplified version where it's no longer undefined, and we come up with 6 divided by 4, and that's 3/2. So the hole is located at 3, 3/2. When I go to graph this at 3/2, I'm not going to draw a closed circle. I'm going to draw an open circle because it is undefined at that point. So make sure when you graph those points of discontinuities or holes in the graph, only when the factors cancel, and you go to graph it, make sure it's an open circle. So our graph, once again, gets close to the vertical asymptote and then the horizontal. And then down here, go through those 3 points as well. And once again, you can see the open circle there. So there's kind of a new part about graphing with points of discontinuity. Now in your book on page 152, there's guidelines to sketch a rational function. And we kind of just went through them, but this might give you a list to kind of look at as you're going through and working on your homework. Number 1, you always want to simplify the function. Okay? And that's going to help you identify what the rest of this stuff will be. Once you simplify it, find your intercepts. Find your y-intercept. If you're finding your y-intercept, you're plugging in x equals 0. Find your x-intercept or your zeros. And so when you plug in 0 for your y value, then what ends up happening is your denominator basically just cancels out, and really all you're doing is finding the 0 of the numerator. Your vertical asymptotes come from the denominator equaling 0 once it's simplified. Your horizontal asymptotes have to do with your degrees. Number 6, check for holes and oblique asymptotes, which we haven't talked about yet. And then plot a couple extra points so you can kind of get a nice smooth curve for each of those. So that's kind of the process that we want to go through when we're sketching a rational function. Alright, on example 3 here, we're going to graph the rational function f of x equals x squared minus x divided by x plus 3. First step, simplify it, if it can be. So we factor to see if it can be simplified. And so we find out on this one that it can't be simplified, which is fine. We just need to make sure that it can't be simplified before we go and find everything. So we find our y-intercept, same thing. If you're finding your y when x is 0, what is y? So you plug in f of 0, so that's 0 squared minus 0 divided by 0 plus 1. So 0 over 1 is equal to 0. So the y-intercept is at 0, 0. Well, if your y-intercept is 0, 0, your x-intercept also has to be at 0, 0, but let's go ahead and find your x-intercept. So what is x when y is 0? So now we say 0 is equal to x squared minus x divided by x plus 1. But because the x plus 1 is going to keep canceling out, I'm just going to set it equal to the numerator. This is a quadratic, so we have to solve. We can solve this one by factoring, and we actually get 2 x-intercepts. And that's okay. You can have 2 x-intercepts on a rational function. You can't have 2 y-intercepts because then it wouldn't be a function. So it looks like our 2 x-intercepts occur at 0, 0, which we already knew, and at 1, 0. So we also have another intercept right there. Vertical asymptote is where the denominator is equal to 0, and so we have a vertical asymptote at x equals negative 1. So I'll go ahead and graph that dotted line, indicating that's where the graph is going to get close to as the y value gets really large and really small. Horizontal asymptote has to do with the degree. The degree on top is a 2. The degree on bottom is a 1. So when the degree on top is larger than the degree on bottom, we do not have a horizontal asymptote. So there's none. And then we get to what's called a slant or an oblique asymptote. So what is a slant or oblique asymptote? Well, it's still an asymptote. It's just not horizontal or vertical. It's basically going to be a diagonal asymptote. So the graph of a function has an oblique asymptote when the degree of the numerator is exactly 1 more than the degree of the denominator. Exactly 1 more. Okay? So when this occurs, we're going to find the oblique by using division. Okay? And so we can divide by long division or synthetic division. It just depends on what the problem is. So we're going to divide the rational function to figure out what that oblique asymptote is. And so on this one, look at your degrees. Is the degree of the numerator 1 more than the degree of the denominator? Yeah, the degree of the numerator is 2, the degree of the denominator is 1. So it's exactly 1 more. So we can find the oblique asymptote by dividing the rational function by taking x squared minus x divided by x plus 1. So how are we going to divide this? Well, we could use long division. We could say x squared minus x, maybe put plus 0 in there, and divide this by x plus 1. That's a possibility. But we also, on this one at least, we can use synthetic division. So we can do 1, negative 1, 0. And then if the factor is x plus 1, then negative 1 will go over there. And then you can use synthetic division. Either one is a possibility. It all depends on the problem. This one you have the option for either. So let's use synthetics, a little bit easier. So carry down the 1, get negative 1, negative 2. You get 2, and then your remainder is 2. Now your remainder actually doesn't matter when you are doing division in terms of finding your oblique asymptote. And so what we have left is, we started with x squared, and so now we're down to a linear equation. If the degree is always 1 higher, you'll always be left with a linear equation. So it's y equals x minus 2. And basically why the remainder doesn't matter is because this line is going to shoot off to infinity, and then that number just basically becomes obsolete. And so your oblique asymptote would be y equals x minus 2. So now you have to graph that one. Well, these are all going to be linear, so you should be able to graph them pretty easily. The y-intercept is at negative 2, and the slope is at 1. So you'll have this, right, as your oblique asymptote, and that is at y equals x minus 2. And so now we just need those additional points that we have talked about. So let's go ahead and x and f of x, look at the graphing calculator and pull some additional points. We have the 2 points, which are the intercepts, but other than that, all we have is the vertical asymptote and the horizontal asymptote. So on this one, on the graphing calculator, I came up with negative 2 has an output of negative 6. Negative 3 also has an output of negative 6. And then 2 has an output of 2/3. So if I plot those, negative 2 is at negative 6. 1, 2, 3, 4, 5, 6. Negative 3 is also at negative 6. And then 2 is at 2/3. So once again, just do the best you can based on that information. It looks like this one will kind of come down here and then go back up. And then this one over here will kind of go here and go back down. Okay, and it's a sketch of the rational functions, but we want to get kind of 3 points in each of those regions to get a nice smooth curve. So I've shown you kind of 2 new things, the oblique or the slant asymptote and the point of discontinuity. Also we talked about, I guess, the x and y intercepts, but those you find the same way that you've done before. So if you feel comfortable with where you're at right now, you can end the video. If you would like to watch one more example of graphing rational functions dealing with oblique asymptotes and potential holes in the graph, then you can watch this last example that we can do. I would probably pause the video, try it yourself, and then come back and see what things that you hopefully got right here. So once again, we want to start by factoring the rational function. So we have x minus 2 and x plus 1 divided by x minus 1. So we have factored it. No factors cancel, which is perfectly fine. Y-intercept, plug in 0 for x. So when we plug in 0 for x, we will get 0 squared minus 0 minus 2, and then 0 minus 1. I plug it back into the original because nothing canceled, so it's just easier when it's simplified out. So it looks like we get negative 2 divided by negative 1, which is 2. So your y-intercept is at 0, 2. The next part is the x-intercept. So plug in 0 for y, solve for x. Your denominator is going to cancel, so we have 2 factors once again in terms of a quadratic. We have 2 x-intercepts at x equals 2 and negative 1. So at 2 and negative 1, so 2 comma 0 and negative 1 comma 0. And when you're writing your intercepts, write them as points. They're points on the graph. Your vertical asymptote is your denominator, where there's factors that didn't cancel, so you still have x minus 1. So your vertical asymptote is at x equals 1. So we will graph the vertical asymptote at x equals negative 1 using that dotted line to indicate it. I also forgot to plot my x-intercept, so let me go ahead and do that at 2, 0 and negative 1, 0. Your horizontal asymptote, your degree on top is 1 larger, so you have no horizontal asymptote, but since you do have a degree on top that is 1 larger, you need to divide x squared minus x minus 2, and once again you can use long division, or on this one it actually works again where you can use synthetic division, so you just have to make that decision what method that you want to use. And so we're not interested in the remainder. So it looks like what we have left is we started with a quadratic and we should end with the linear. And we have y equals 1x plus 0 or just y equals x. So your oblique asymptote or slant is y equals x. And so when we go to graph that with a slope of 1 going through the origin there. Not the best line, but y is equal to x. And then we want to get a couple additional points in there as well. So let's look at the graphing calculator and pull out some points that we could use for this. And so I have a couple. I have x equals -2. Then the y value would be -1 1/3. And then if x is 3, we get 2. So I already have a total of 3 points on there based on the intercept. So I found a couple more. At -2, it's at -1 1/3. And then at 3, it's at 2. So maybe I could get one more potential point on that other side there when I have the 2 points, but this will work in terms of getting the sketch. So as we sketch this, you can see it's going to get close here and here to the oblique asymptote, and same thing on this side, it gets close and then goes close to the vertical asymptote. So there's another example of graphing a rational function, going through and finding everything algebraically. The really only reason you guys will be using the graphing calculator is to find those additional points. That's really the only reason you need it. Everything else you can do algebraically.